Hiya! So today we're going to look at an example, or in this video we're going to look at an example, and we're going to break down basically the Poisson point process. We're going to figure out what these two different ideas are, how they work, what this means. It's hella confusing, but I think once you see an example, it's all going to be like, oh, I still don't understand, but I kind of get it. I think it's one of those things you just got to try a few things and maybe it'll eventually sink in. It's definitely a little weird. So normally the standard way to look at this is through phone calls. But I feel like at least me personally, I never make phone calls anymore. I'm just like, yo, I'm going to send a DM. So we're going to do this by DMs instead. And we're going to suppose you're actually super, 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 super popular, like your celebrity status now. So you get roughly 3 DMs per minute. So this is the key piece of information, 3 DMs per minute. So what the first thing I should clock when I look at this, what I should see right away is per minute. So minute is my unit of time. So I'll note that on the side. So what we can do is let's set up some variables and some things and kind of figure it out from there. So first, we're going to look at things from a Poisson distribution way. And then we'll look at an exponential distribution and start asking questions. So first way was Poisson. And we basically want to know, okay, in some interval of time, how many DMs do I get? That's basically it. So since we're talking about per unit as our measure, our unit of time is just 1 minute. I is going to be some number of minutes. So for example, here I might say 2 minutes in the future to 6 minutes in the future, right? This might be an example of some interval. Then we're going to say, okay, so in this case, I know it's going from 2 to 6 minutes, so we know our interval here is 4 minutes long, right? So our t, in this case, is 4 minutes for the interval. Then we're asking, so then our Poisson distribution is parameter. So if we recall from before, we look at its lambda t. So what's our lambda? Well, I've already given the lambda. We get 3 DMs per minute, right? So 3 DMs per minute basically gives me the lambda, 3 per minute. So we have lambda t is 4 times 3 is equal to 12. So that's it. So it's a Poisson distribution with 12. So Poisson distribution, if you remember, this is, now I have to remember, e to the minus, I guess here we have lambda t. Then we have lambda t to the k over k factorial. Right? So normally we have mu's instead of lambda t, but here we have lambda t. So here we would have e to the minus 12, 12 to the k over k factorial. So this is our Poisson distribution. Now the second way of looking at this is using the using exponential distribution, right? So in this case, what we have is we know that we get 3 DMs per minute. So in other words, we get a DM roughly every 1/3 of a minute, right? And so in this case, this means our expected value is 1/3. We get a DM every 1/3 of a minute. And we know expected value in this case, expected value, I can't write, expected value is equal to 1 over lambda, right? So here we get 1/3 is equal to 1 over lambda. So in other words, from before we know the exponential distribution is going to give me with rate lambda is equal to 3. So it's the same lambda as before. And so remember here the exponential distribution is given by lambda times e to the minus lambda t. So in other words, we have 3 e to the minus 3t. So you should see right away these two are not the same. Not the same. Don't look the same. Don't look the same. But I guess here technically I should use t's as my variable, but anyway. So first let's ask one question. So if I ask the question, and let's try to figure out how to answer these questions. So the first question is, what is the probability that you get 0 DMs in the first 4 minutes. Okay, so here I'm counting how many DMs I have in some interval. I'm given an interval of time and I'm saying I have this many. This should right away make me think, oh, I'm looking at number of points. I don't care about when the points happen, I just care number. So this should make me think, oh, Poisson. So what this says is, okay, if I'm looking at Poisson, I need to set up my interval I. In this case, I have first 4 minutes, so I is equal to 4. Basically, t is equal to 4, 0 to t is equal to 4. So I is equal to, sorry, it's an interval, sorry. So this is 0 to 4. We're asking for 0 dn's. So we want basically k to be 0. In other words, we're asking the probability that n of I is equal to 0. And here we said that this is given by the Poisson distribution. Poisson. So this is equal to, we plug in our formula. So here we have e to the minus 12, 12 to the k. K here is 0. So 0 over 0 factorial. And we just solve. So here we basically have 12 to the 0 is 1 over 1. So we have e to the minus 12, which is roughly 0.00001, 2, 3, 4, 5, 6, 1, 4, 4. 5 zeros. Okay. Now so that's one thing solved. Nice and easy. So let's ask now a different question. So the next question I'm going to be asking is, what is the probability that we get our first DM after 4 minutes? So in this case, what we really want is we're looking at t is equal to 4. And here we're really talking about first DM after 4 minutes. So here you should think, oh, I'm looking at time intervals, as in like, when is the first time something happens? So here you should think, this is an exponential thing. This is not a Poisson thing. So in this case, we're going to be looking at, well, okay, when is the first time this is greater than, Yeah, so we want to look at when we have t greater than 4, right? So we want to say when is the first DM after 4. So we want to see when t is greater than 4, where t is time to first DM. Okay? So here we have, what's our formula? We have 3 times e to the, wait, this is wrong. This is not 3 times. This is just 3. Eek. Yeah. So we end up getting e to the minus 3t. Why is this not right? There we go. E to the minus 3t. Here my t is going to be 4. So we actually plug in 4 here. Oh no, this was correct. I'm an idiot. Because this is the density formula. And then this is, yeah. The formula here, remember, is P of t greater than a. And here my brain was not working. Is equal to e to the minus lambda a, right? Yeah. So here we just plug in a. So it's minus 3 times 4. So it's e to the minus 12, which is also 0.000006144. And if you notice, these two are identical. Same. Why? Well, let's think about this for a minute. Let's look at our two things, our two sentences, our two questions. The first one is saying, what's the probability you get no DMs in the first 4 minutes? And the second one is saying, what's the probability that you get your first DM after 4 minutes? Well, if your first DM is happening after 4 minutes, that means you've gotten 0 DMs in the first 4 minutes. These two questions are asking the same thing, but in two totally different ways. And that's why it makes sense that these numbers are the same. The difference is, and this is why I said these don't look the same, because they technically aren't the same, because we have to plug in different numbers depending on how we're working with things. For example, here on top, I had to plug in 0, and the bottom one I had to plug in 4. And so this is kind of where you have to kind of interpret things in a nice way. And this is definitely not an easy thing to do. But hopefully in the next 3 examples we kind of go over, this should make a little bit more sense. So let's kind of look at 2 more questions or 3 more questions. And then, so this video might be a little longer. But hopefully that helps solidify some of these ideas. And then we'll end this video after these 3 questions. So the next question is asking, what's the probability that you get no DMs in the first minute and then at most 3 DMs in the second minute? Okay, so this is breaking shit down. Oops, sorry. This is breaking stuff down. So we get no DMs in the first minute. So what this is saying is, okay, in the first minute, I get no DMs. This part is going to be Poisson, right? So this is saying in the interval n of 0, 1, we get 0 things. Then we get and. Then we ask that then at most 3 DMs in the next second minute. So basically this is saying in the second interval, 1 to 2, I get at most 3 DMs. So less than or equal to 3. Now here, one thing to notice is since these are 2 different minutes, they're independent of one another. It doesn't really matter. So what we can actually do is I can just, I'll leave these, but these are independent events. So let me actually move this. Is this, oh, it's going to bring the line. Damn you. Can I just remove the line? Oh, bananas. Oh, well, close enough. And then at most 3 DMs in the thing. And then we'll highlight this again, and hopefully that'll be okay. Cool. So this is basically giving me P of n 0, 1 is equal to 0 times P of n 1, 2 less than or equal to 3. So this one here, we kind of already know, right? This is just from above, but we have the interval here is 1 instead of, oh, yeah, so I guess I didn't mention. Rewind. Why is this 12? So the 12 here is coming from this t is equal to 4. So we had plugged in t is equal to 4 here, right? Because we had lambda times 3, t, 4 times 3. So that's why. So in this case, we'll still have e to the minus 3 times t. No, this is exponential. No, sorry. This is thing, and then it'll be times by mu. So 3 times t to the 0 over 0 factorial. So this is this part. T is equal to 1 in this first part. T is equal to 1. Here t is equal to 1 as well, right? Because the interval is length 1. Length 1. And so this part here gives me e to the minus 3t as well. And then we have to sum up from 0 to 3, right? So we get 3t to the 0 over 0 factorial plus 3t to the 1 over 1 factorial plus, so t is equal to 1, so I'm just going to keep these out from now on. 3 squared over 2 factorial plus 3 cubed over 3 factorial. And we multiply these together. So this is just, I'm out of room, so we'll do it this way. So we get e to the minus 3 times e to the minus 3. This becomes 1. This is 1. This is 1. This is 1 over 1, so this is just 1. No, it's 3 over 1, so it's 3. This is 9 over 2. And this is 27 over 6. So this we get 1 plus 3 plus 9 halves plus 27 over 6. Plugging this into a calculator, we end up getting is equal to 0.03222, and that's it. So it's roughly 3.2% that will get no DMs in the first minute and 3 DMs in the second minute. It makes sense that these are low because we're averaging 3 DMs per minute, right? So just the chance of getting no DMs in that first minute is really hard. Okay, so that's the next thing. So let's look at the next problem. What is the probability that you get no DMs in the first minute and the wait time between your second and third DM is more than 2 minutes? Okay, this one's a little more complicated, but we can do this. So again, we're asking probability that you get no DMs in the first minute. So the probability, so again, this is an interval thing. So we're going to think Poisson here. And time between second and third DM is more than 2 minutes. So in this case, we're looking at the time being greater than 2, where t in this case, time between second and third DM. Now notice how these must also be independent. Now why? Well, if I didn't get any DM in the first minute, that means my first DM is going to happen after the first minute. And so my second and third one, like it's not like it's how do I explain this? Like they're no relation with one another, right? The time between the second and third one has no relation as to whether or not we got a DM in the first minute or not, right? I don't care how long the time is between them. Even if that part comes into that first minute, they're not related to one another. It's a little weird to think about. But basically the timing doesn't care about when something happens. So basically what we end up having is this times the probability that t is greater than or equal to 2. So this one we've done a few times, and we already know that this is equal to -3. Here we already know p of t greater than 2, right? We already did this. Oh wait, no, this is wrong. So it should be e to the -6 times e to the -3 times 2, so it's e to the -6, which means my number on here is wrong. So let me quickly, these two added, -6 is e to the -9, and with a calculator, this will give me 2, 3, 1, 2, 3, 4, 1. So a fairly small number. All right, so finally, we're going to look at this fifth problem. So the fifth problem is saying, what's the probability that your fifth DM takes more than 4 minutes to arrive? So this might be a little weird. There's, again, many ways to look at this, right? We can either look at it as, okay, well, the fifth DM, we just need the time for the first, the second, the third, the fourth, and the fifth. So if we let ti equal time until ith DM, what we're asking is we want to say what's the probability that t1 plus t2 plus t3 plus t4 plus t5, so time until the fifth DM is greater than 4. Or we can look at an interval and we can say, oh, well, if we want the fifth DM to take more than 4 minutes, well, we can just say, okay, what's the probability that the first 4 happen in the first 4 minutes? Or at most 4 things happen in the first 4 minutes. So another way to write this is, what's the probability that inside the first 4 minutes, we have at most 4 things, because the fifth one has to happen after 4. This one is much easier to calculate than the first one, right? The first one is hella complicated, has all these additions. So we'd rather do this, right? So this 4 here is basically telling me, I'll do it here. We have e to the -3 times 4. And then we have to do this 4 times. So we end up getting 3. So 3 times 4 is 12. So we get 12 to the 0 over 0 factorial, plus 12 to the 1 over 1 factorial, plus 12 to the 2 over 2 factorial, plus 12 to the 3 over 3 factorial, plus 12 to the 4 over 4 factorial. And this, if you end up plugging into a calculator and trying it out, we end up getting e to the minus 12 times 1,237, which is roughly 0.0076. So you have a 0.76% chance that your 5th DM will come after 4 minutes. So yeah, so as you can see, these can be a little confusing, but the nice thing is there's more than one way to look at things. So this is one of those cases where if one way looks difficult, for example, this way looked difficult, then you might be like, oh, well, let me see if another way might be easier. And this is the big thing about distributions, and the nice thing, in that sometimes looking at a problem in a different way turns a very difficult problem into a super easy problem. So that's one thing to kind of consider when doing kind of just normal problems. So we'll stop here. This video is exceedingly long. Sorry about that. But I really wanted to get into this problem in the nitty gritty. So yeah, so in the next video, we'll talk about Erlang's distribution. So I will see you then.